expression.
Well, thanks, Steve, and the organizers for having me over here. I was a postdoc, like maybe many others here, a long time ago, and it's really great to be back in this inspiring place. I will give a talk which I think is probably, by the standards of KITP, as I know it, as of 10 years ago, a very technical talk. So I hope I will get my message across. I think it's not that difficult to understand if you have a background in physics. So my talk is about the operator product expansion, which was proposed by Wilson, as far as I know, a very long time ago. And it basically says that if you take a correlation function, which is this angle, this bracket here, you insert some operators which I call O, so these are composite fields, and they may have various they have a labeling the various kinds of operators, and their tensor indices or spinor indices, etc. You have those and a couple of spectators, which are likewise operators. Then you can, what the claim is, you can expand such an expression, so you can factorize such an expression in terms of certain numerical coefficients, or C, operator product expansion coefficients, together with the expectation value of just this one-point function. So there's a sum involved here. So the sum is over the set of all operators that appears on the right side. So when it was proposed, the idea was pretty much that it's a short distance expansion, which means that the idea is you scale all these points towards a reference point, which you can take, for example, to be the last one or the center of mass point. It doesn't really matter for me; it's always the last one. So in this way of thinking, it's a sort of factorization of this correlation function into a short distance part, which is this bit, and a long distance part, which is sort of this bit. And sort of so this operator product expansion is a technical property of quantum field theory, which sort of basically says that you have some sort of factorization if you have a wide separation of energy scales, so short versus long distance. And so it has found several practical applications, most notably for deep and elastic scattering in asymptotically free series. But sort of from a conceptual viewpoint, it also plays an important conceptual role in especially in conformal field theories. I just mentioned this kind of word conformal bootstrap, which I guess has become popular again recently. And it's also sort of from a mathematical viewpoint, it's also the structure that's really underlying various mathematical formulations of two-dimensional conformal field theories. The buzzword is vertex operator algebras. So I like it very much because it's very natural if you consider field theories in curved spacetime. And the point is really that in curved spacetime you don't have a distinguished vacuum state, so you have a whole bunch of states, and these states will depend on complicated boundary conditions and so forth. So it's nice to have a formulation which is of the theory which is independent in some sense of all that, and that arises because these coefficients here, they depend only on the local geometry near a point, whereas this kind of infrared object depends very much on boundary conditions, on choices of vacuum state and so forth. So in this talk, this is sort of an old story. I haven't said anything that was really new. What I want to do is, what I've been interested in this expansion, what I've been working on with my collaborators is I really wanted to nail down some definite properties of this expansion. And the first question that really comes to mind is the question whether this expansion converges. So if I let me go back. So by expansion, of course, you can do many expansions in quantum field theory, large N coupling, and so on. So by convergence, I mean really the sum here over the various composite operators with increasing dimension. So this twiddle is really, it's really supposed to clarify what this twiddle sign here.
Are you working in Euclidean space?
Yeah. So I'll state all my technical assumption. And then the other nice feature of this operator product expansion is that in some sense it gives an algebraic skeleton of quantum field theory. So it allows you to formulate something like associativity or consistency conditions, which are in some sense at the heart of the bootstrap approach. And you can ask sort of what can you actually say about these kinds of conditions if you have, for example, a non-conformance theory. And then my last point is a sort of new kind of recursion identity for this condition. Okay, so my point is really to nail things down as much as I can, and for that I need a specific model. And because this one is simple, I take the phi to the 4 model. So this is just a phi to the 4 interaction in 4 Euclidean space-time dimensions, and I treat this perturbatively, not because I like it very much, but because that's all I can do. But you can do at least that precisely. So just to say, in this model, correlation functions are defined in the usual way. So you take your action and you stick it up in an exponent with a minus sign, and then you put in your composite fields, and you pass integral with some sort of normalization. And if you really want to define it, you have to subtract various counterterms to make it finite. And in my model, the composite operators are just products of the basic fields and possibly their derivatives. So I won't bother to write it out, but this will have a bunch of tensor indices and so on. So these have to be renormalized as well. So how these operator product expansions are then defined in the usual way, a la Zimmermann from 1970, or another approach due to this gentleman's. So they're defined in some way. And so really how I define the theory, I just do it brutally. I brutally introduce an infrared and an ultraviolet cutoff, and then I derive renormalization group flow equations for all quantities like correlation functions, operator product expansion coefficients, and so on. And then I solve brutally this. I integrate these renormalization group flow equations, and these in particular define the quantum. So it's a method that goes back to the classic paper of Joe. Beautiful paper. So that's the basic machine. You you have to put on. It becomes a little more baroque if you apply.
Isn't this theory supposed to be trivial when you remove the cutoff?
Perturbatively. You're referring to the Landau ghost?
Yeah.
Yeah, non-perturbatively that's true, but you can still do everything to L loops and ask whether something is true at L loops, where L may be 1 million or something like that.
And why do you need an infrared cutoff if you have a mass?
Oh, that's just the method of this renormalization group flow equation. You define it like this, and then you differentiate everything with respect to this infrared cutoff, and then you derive a flow equation, which you integrate subject to boundary conditions, as explained in this beautiful 1980s paper. Okay, so my first result is the following. It's a kind of factorization, and so the idea is I think most easily explained in the following. So if I have, let's say, 3 points, 1, 2, 3. So I can have like an equilateral triangle, and I have 3 operators, O, 1. Okay, so I can have an equilateral triangle, or I can have a sort of very degenerate triangle. So and it's kind of clear that if you have sort of a degenerate, the points in this sort of degenerate configuration, then it should be possible to first expand the product of these two operators and then subsequently expand the rest. And that's basically what this is saying, except that I do it for n points. So this right-hand side is where you expand things subsequently. So first do the product of 1 and 3 and then the rest. And this is where you do it all at once. And there's a condition which is basically saying that your triangle should be a little degenerate, like this. So, but just slightly degenerate is already fine. So if it's sort of an equilateral triangle or something, then this quantity is sort of is small if the triangle is very degenerate, and it's sort of order 1 if it's not degenerate. Yeah? This sort of gives you how degenerate this is, and it has to be a little degenerate, otherwise the sum does not converge. So it's an absolutely convergent sum at each fixed order in perturbation theory. So you take the left side as L loops and the right side as L loops.
So does it matter that you're doing this bleeding?
For technical, yeah.
What is the sum over C?
So C are the labels. So the operators, you have lots of composite operators like phi squared, phi to the 10th, and so on. And these capital letters A, B, C, D tell you which operator you have. So it's the sum of the intermediate operators. So this again, what I said about these triangles. Epsilon is this number here, which is the maximum or the minimum distance, and it's this for a degenerate triangle. It's much less than 1 and 4.
For an equilateral triangle, you know that it doesn't work?
Well, it definitely doesn't work.
Okay.
So if this side is even fatter, then it doesn't work. So the consistency comes about because if you have a triangle like this, so then this is the shortest side, so you can, surely you can really see this. So you can first expand these two operators and the rest one. But this is still shorter than this one, so you can also first expand 2 and 3 and then the rest. Both give absolutely convergent series, so you get an associativity law that way. You get a non-trivial domain of configuration of 3 points where you get this associativity law. So how you prove this, you really estimate the left side minus the right side with the sum carried out to some large order, and you really show the remainder is small. That's a bit complicated.
Do we have to think of this as strictly applying for vacuum correlators?
No, it's
ground state correlators?
No. It's the coefficients themselves. It's like an associativity condition in an algebra. So it is a condition. So these 3 operators could be inserted in any state. So maybe let me. So the second result that we have is about the convergence of the expansion itself. So what I've written here for you is again a product of n fields. And then I have a couple of spectator fields. And the hat just means I Fourier transform the spectator field. So this thing you should think of as like an n particle state or something. And then I approximate this product of n operators with the operator expansion carried out to some high dimension d, but finite dimension d.
Those p's are arbitrary.
Well, yeah, so there can be, one has to be a bit careful in massless theories, but so far. Okay, so then this is sort of the remainder of the operator product expansion. So you don't expand it out all the way, but you stop somewhere, which is what you do in practice anyway. So you want to know if that approximation is good or in what sense it is good. And the bound, which you obtain using this renormalization group flow equations, is what this. So this looks a bit complicated, but all terms mean something, so I'll break it down for you. So first of all, you have a capital P, which is the maximum momentum. So it's the largest momentum of the particles. So it's the energy of the state generated by the operator from the vacuum, if you like. Then you have a mass scale. And so that mass scale is just the mass of the theory, v⁴ theory, if it's a massive theory. And if it's a massless theory, it's a much more interesting and tricky case. Then it's a renormalization scale. Yeah, so scale. And so you see right away from this.
I have a question about this. So
yeah.
Am I supposed to view those operators as integrated over space, or am I supposed to view them as inserting particles at infinity?
No, they really insert it over space. So you take the phi of x1, phi of y1, and so on, and then you just Fourier transform.
Imagine that the operator corresponds to change in the coupling constant of some theory, let's say n equals force per unit.
You mean this one?
Yeah.
Oh, this is the basic field. So the basic field. So the interaction. So the Lagrangian is like del phi squared plus. And then there's a coupling G. And this phi is the basic field. So the changing the Lagrangian would be inserting phi to the 4.
Why not
I mean, what bothers me is that if you change the value of phi in the middle, it could be changing the coefficients because it would depend on the. Well, if it was the coupling, I mean, my question was more precise. Was the coupling?
Yeah, for the coupling. Yeah. Well, maybe let me explain my bound first. So I think let me while I'm talking of processing. So first of all, you see that if the energy of the state, if you allow me to use these words, becomes big, so if P becomes big and then D is some number, R is the loop order or something, then this remainder gets big. Yeah. So that's basically saying if the energy of the state in which you're doing your operator product expansion is high, you get a bad approximation. The higher the energy of the state is, and that's plausible because it's a phenomenon of separation of scales. Yeah? So you need a smaller. So then you have.
What is kappa?
Yeah. So kappa is. I'll say just in a minute what the kappa is. I'll explain everything. So then you have the maximum of the distance of all the points over some minimum distance. So basically, if the triangle. So the maximum over the minimum is something like, again, the eccentricity of the triangle. Yeah. So if you have sides which are much shorter than the average sides, then the minimum is much smaller than the maximum. Then the convergence again is bad. So you don't want eccentric configurations of points. Yeah. Over 3 points is the triangle. Then you have a 1 over d factorial. So the d is the order to which you expand your operator product expansion. So basically, if the d gets large, then this factorial wins against any power here. That's the point. So, and the kappa, which you asked about, is the infimum of, is an energy, has the dimension of an energy, and it's the infimum of the renormalization scale, usually the mass. And then you have in massless theory the phenomena of exceptional momenta. So if some subsets of these momenta add up to 0, that you call an exceptional configuration. If you do amplitudes, you always know you get some bad infrared divergence. So the epsilon is sort of how far you're away, or basically the kappa is how far you're away from an exceptional configuration. If the theory is massive anyway, then there are no troublemakers, so that's why it's the infimum. Yeah? So for massless theory, this is a very harmless quantity, but for massless, it's a non-trivial bound only if the configurations are not exceptional.
So this is only for phi to the 4th, or it's?
Oh, only for phi to the 4th. So again, how you prove this is you derive a flow equation, renormalization book flow equation, you integrate it, and you make some inductive bounds, and you show that these bounds reproduce themselves.
Is it obvious that the right-hand side is small and the x is large?
Yeah, so it's if all the axes, if you have a triangle and you just shrink the whole thing, just multiply everything by a conformal factor or something, then this d wins against those, and so then this number gets small. So d is the order up to which you expand the operator for expansion, and the a's are just the sum of the dimensions of these.
But the P,
So the d would be much bigger if you want a good approximation than the a.
but the super P can overcome.
Yeah, so it's
Yeah.
there's a competition of effects here, really.
Oh.
So the exceptional momenta can also be bad. That's why.
Everything scales the same way. Does it work? I mean, if
No,
P is
the P
over
is
1
fixed,
over
so you-
delta x.
So the main question here that we asked, first of all, does the expansion converge? And again, I write that the OPE remainder is less than this, so the convergence of the expansion follows because basically the factorial beats everything else if everything else remains. So the square root of factorial still beats everything. The factorial beats any power. That's the convergence. And for massive fields, so the bound is finite for an arbitrary configuration of momenta. You don't have to worry about this exceptional momenta. And for massless fields, everything is just infinite anyway for momenta. And as I said, the bound vanishes as d goes to infinity, which means the remainder goes to 0, which means by definition that something converges. Yeah? So a surprising fact, I think, is that the OPE expansion converges for small but finite distances. It's usually thought that it was asymptotic only, but it really converges even for very large distances. Yeah, it just converges extremely slowly. So it takes a long time before the factorial wins against the power. Or if it's a large number to some high power, it takes a very long time to
The limit P goes to infinity and D goes to infinity commute?
Well, P is just the energy of the state. You wouldn't want to let that go to infinity.
But would the limit, if I would look in both, would they commute the limits?
Oh, I don't know. It's
If you
complicated.
did this in 3 dimensions rather than 4, would the convergence be then better?
So you mean the differences between super renormalizable? Yeah, then it was super renormalizable. It's much easier to see that who wins. So it's the renormalizable case where there's a real competition of it.
But coming to the question of Eliezer, I mean, you have a P and you have delta x, okay,
Yeah.
typical separation of it. So, I mean, how can...
So the
first the convergence is there no matter how large is P?
Yeah.
Relative to 1 over delta x?
It's just very slow.
Usually it's easier to prove this not for these physical states or formulae, but rather for fields in position space.
Yeah, I think, so I have this other result with the factorization, which you can really think about in that way. We did it with, I think, because physicists like to talk about momenta, and so I thought this was a nice, but maybe you're right. So the convergence is slow if the energy of the state is large, if the maximal distance of the points in position space is big compared to a reference point, it's also slow convergence. And I explained this difference between degenerate configurations that always works against you if you have this degenerate. Okay, so you can also do something if you don't like these exceptional configuration, you can do something like a wave packet rather than something like a sharp momentum. So technically you take the spectator and you integrate it against some profile. Yeah, so it's like you take the F to be in positions in momentum space, localized around some fixed momentum, but smooth out. And then you always, the statement is you always get a finite answer basically you get a similar bound with some so-called norms. This is mathematical thing. It's just numbers that specify the size and shape of these wave. Yeah? So it just shows that if you really do wave packets, then really the exceptional configurations are not really a problem. That's the point. Yeah. So they're more like a problem that you idealize. You want waves with a sharp and fixed momentum. Okay, so mathematically, this is some talk about. Okay, so the last point I want to talk about is if you give me, you said basically half an hour, so.
Yeah, I think that's allowing for discussion.
Yeah,
certainly.
Yeah. A few more minutes. This is my last issue.
So
usually, what I said, how I define these things, I brutally put in a cutoff. The cutoff did not appear anywhere anymore because in the end it was taken to infinity. But if you open the hood and you look how these things are derived, you have these cutoffs everywhere. So we use this Wilson-Polchinski flow equation method to define these things in the first place. But I want to point out there's a way to get these operator product coefficients just from themselves in some sense. There's a nice recursion formula, and this is the following. So G is the coupling constant. Is the derivative. This is a statement about the derivative of a OPE coefficient with respect to the coupling constant G. And so what is this? So if you have a correlation function and you differentiate with respect to a coupling, you get an insertion of the corresponding operator. And so you do get a similar term here. So the phi to the 4 is an additional insertion. I mean, maybe it takes a bit time to get used to this. It's just a coefficient with one argument more, and it has this insertion. But then if you were to integrate over the position of this insertion, you'd get a bad divergence, actually, because you have phi to the 4, and the A's can have arbitrarily high dimension. So that cannot be the only term. And it turns out there's a couple of other terms that are there anyway, which precisely cancels off this divergence. And I think I have. Okay, so why is this a recursion relation? So you can expand in powers of G, and then obviously you get a recursion relation. So let's call it a recursion relation. The starting point of the recursion is, of course, the zero loop, so the free field theory, and then you do. Okay, so the nice thing about this, I think, is that it does not involve, if you want to calculate it, it does not involve anymore the correlation functions themselves. You just, if you think these really are the structure constants of the quantum field theory, this is a nice equation just for the structure constants. And it's also, by contrast to other equations of this sort, like a Dyson-Schwinger equation or something, it's a really well-defined equation. You don't have to do some by hand renormalization, and maybe that's the last point I want to explain. So this is the integrand, the right-hand side. So it looks a bit complicated, but basically I have 2 points, and then I have the insertion point, which I want to integrate. And so if you just look at this term, and there are 3 dangerous regions. Basically, if the insertion point goes far out, so because it's an infinite volume to integrate over, that will in general diverge. It's infrared divergence. And then if the insertion point gets too close to the other guys. So this is these 2 circles. And so very roughly speaking, there's a UV region like where the insertion point gets close to this one. And then, by my factorization theorem, though, this thing factorizes. And what it factorizes into is precisely this. So in this region, the divergence, this is cancelled by this term. And then there's another one where the divergence is cancelled precisely by another term. And then there's the infrared region, where you can also have a divergence, well, in general you will have a divergence. And then there's the third term, which precisely
These formulas involve the scaling dimension of the operators.
Yeah.
I guess I don't know much about this, but are you assuming, or is it known that those dimensions are not themselves sort of scale dependent? And so if they are scale dependent, what scale do we evaluate them at in using the formula?
So, well, basically, if you have two operators, you let the points coalesce. You're going to get some divergence, roughly, yeah? So which is to leading order up to logarithms or something like that, just given by the naive power. You know, some operators have some dimension, yeah, so and you some length dimension of length, and the divergence to leading order is given by this. So if you have two free fields,
you're saying that's not it doesn't involve the anomalous dimension?
No, it is. It is. So I didn't say it was a power, yeah. So I didn't. So these have divergences which are surely more complicated than this. The simple. But the cancellation I was just talking about the cancellation of the divergences that occurred. Yeah? So I didn't say there are no anomalous dimensions. That's wrong. So these are very complicated functions. Yeah. So but basically, you have two operators. That's precise. So you have 4 dimensions. That's the leading. So this counts as having dimension 1 and counts as having dimension 2. And this is correct.
But since you're working perturbatively, your main theorem, you use the canonical engineering dimensions.
Yeah, so it's just as a label. Yeah, so in my main theorem, just as a label, but I'm not saying so in loop order, of course, everything has these logarithms as well. It's just to keep, just as a bookkeeping number here. Okay, so I wanted to finish this technical talk here. I think the most interesting question, of course, is what you do with gauge theories, but that is not really such a big deal if you understand master theory. So these results all also generalize relatively straightforwardly to curved Riemannian manifold. So if instead of a Euclidean space, you have some some curved Riemannian manifold. So it's not so obvious what happens in Minkowski space, because there you have the operator product expansion, but you also have singularities on the light cone. Yeah? So this is sometimes called light cone expansion. There we don't really know. So my vision, so Santa Barbara is a place of vision, so I think this operator expire I'm interested in it really is because I think it gives an alternative strategy to define quantum field theories. And this last equation with the it looks complicated, but I think once you understand it, it's not complicated. This, I think, it's derived in perturbation theory, of course, order by order. But you can hope that it might also hold non-perturbatively, because once you write it down, there is no more reference to any perturbative expansion. And so we think that, for example, in the Gros-Neveu model, in 2 dimensions, you can really solve this equation and at a non-perturbative level, and show that you can really integrate this equation non-perturbatively. In that case, the fermions help because of the Pauli principle. So my vision is that this may be a way, an alternative way, maybe, to define quantum field theories. Okay, maybe let me.
Well, we do have time for questions, discussion.
Did you consider doing phi to the 4th in large n for a vector model in 4 dimensions? Because there are non-trivial results there.
Yeah, well, depends. I mean, if you have vector large n, speaking, somehow you can see from the Feynman diagrams it becomes a bit sort of much more trivial. The large n limit becomes a much more trivial theory. So
It's not trivial for
so at large n, of course, you can take if you take a gauge theory like a Yang-Mills, this equation, if you take these operators to be suitable single trace normalized by suitable powers of n, etc., then this is also a valid equation for the large n limits of these things. And then I think this, again, if you solve this equation iteratively, it really converges. Then the iterations really converge. Yeah. So, but I think that's not maybe so unexpected because the number of Feynman diagrams for large n limit goes polynomially, not factorial. So that's the combinatorics. That's simplified. But it's a valid equation for the large n limit in the adjoint representation, not directly.
So I understand that you might have trouble with this estimating remainders in the Minkowski case, but this formula here, recursion formula, shouldn't you expect that it should hold in Minkowski if you just rotate? Meaning to rotate?
Yeah. Well, I hope it holds. I don't know because, again, if you have an insertion point, you will now also, this thing will be singular when the insertion point comes on the light cone of the other points. And you will have to have a similar factorization then for this so that these divergences cancel. And I don't know if that occurs. I think it occurs.
So you're saying this might not be finite?
I don't know. It's a bit tricky. With the light cone, you also... So the light cone thing, you can think a little bit about. You take 2 points, and then you apply a large boost to one point, leave the other point fixed, and scale the point at the same time. So you move onto the light cone. So you see from the boost, so if these are all also have tensor components, some plus tensor component will be scaled with a positive weight, and some minus tensor component with a negative weight. And then you have from the overall scaling something, so you see that the so-called twist will be the kind of thing that replaces the dimension just from.
But I mean, intuitively, if you look at Euclidean and kind of Lorentzian field theories, they have the same kind of terms.
Yeah, but the thing is, these operator coefficients and the correlation function, they're very, very complicated functions of n points, and they have cuts and everything all over the place. And of course, you can say that you recrotate, but the bound does not. There's no reason why the bound should behave simply under recrotation.
I was just talking about the recursion relation.
Yeah, but you see, the recursion relation depends on this factorization. Yeah.
In the two-dimensional case, you say you can solve the equations just for the large n limit?
No, even for finite n, for the Gros-Neveu model, just for the Gros-Neveu model. And what helps is the combinatorics, the Pauli principle, because you get, of course, from the correlation functions are basically determinants, and determinants have pluses and minuses, so to speak. And if you do it smartly, you can take big advantage of that.
Other questions? Steph?
Yeah, I just wonder what remarks you might like to make about the curved space, issues in curved space application.
I think it's the curved space situation is not really that different. So the coefficients of these operator coefficients now are not just Lorentz invariants, but they also depend on the curvature of the manifold near a given point. But other this factorization, short versus long distances, that occurs as well. Yeah. So in some sense, in the limit, as the points are arbitrarily close, you see flat space, but at a small but finite distances, you see curvature corrections. So these coefficients depend on the curvature, Riemann curvature. You can derive very systematic expansions, but it's...
But you might have infrared issues in the sense that you might be able to remove the infrared color.
No, that's the point. So this recursion relation renormalizes itself. So it automatically gets it's built in such a way that all infrared divergences and all ultraviolet divergences automatically cancel out. And that's in flat space or curved space. It doesn't matter. So yeah. So that's what I thought. So you have these various terms, and in these various regimes, they cancel each other. So it's a sort of, this kind of equation renormalizes itself, so to speak. Yeah? So you don't have to do something else, like with the counter term, or do some other fiddling around. It's automatically okay.
Anything else?
So this is part of this is part of a general. I mean, various people have talked about defining quantum field theory just using the OPE plus other things. Do you know of anyone who's actually tried to do that in some rigorous sense?
Yeah. So of course 1 + 1 dimensional CFTs. When it's basically in many cases it can be reduced to an representation theoretic problem. I don't know. Of course, you know the bootstrap program. That's you try to solve some consistency conditions, but you don't have a very good idea how to solve it.
Right, but those are for CFTs.
Yeah, those are for CFTs.
And those really have.
I don't know. We try to get an equation that would maybe lead us somewhere, and we are hoping. That's all I can say. And it seems to work for the Gauss-Neveu model, which is a model with non-perturbative effects and all that. I mean, but it's a much simpler model still than the gauge theory. So my impression is people have not. So there's this representation theoretic ansatz. There's the brute force. You try to solve this consistency relation, or sometimes called crossing symmetry, which are my associativity. I think there you have to have a really good idea how you're going to get a solution. So it's not like you find Lie algebras by solving the Jacobiad. It's not. You just don't do it that way. So I don't know. So this is one way. I think it has advantages over. Of course, you could also say, why not use the Schwinger-Dyson equation to define the theory? And I think the key advantage here is that with the Schwinger-Dyson equation, it's really, you have to still renormalize it, and it's not an internally consistent system, I think, for that reason. So that's the big advantage here.
I thought you and Bob Wald actually used the OPE to define interacting field theory in curved space-time. Is that not? Is that a misimpression?
Well defined. I mean, you can.
Was it a framework, but it wasn't shown that any actual theories existed?
No, the point there was really just. I mean, you have these general theorems like spin and statistics and PCT. So in curved space, you're a little bit if you look at how this is done, it uses usually the vacuum state very much in Minkowski space. So we were thinking, if you want something like that in curved space, what would the statement be in the first place, and how would you argue that is true in general? And we provided such an argument based on the operator expansion, but assuming such an expansion exists, we didn't define it. Nobody can define interacting field theories in 4 dimensions so far.
So you're saying it's an axiomatic framework?
Yeah, that was just, we wanted to see how you could show something like spin and statistics and PCT. How would you argue that in a curved space? What's PC and T in the first place? It's not so clear if you don't have reflections. So that was the point of this. So this is much more getting quantitative bounds in perturbation theory on remainders, and maybe getting some equations which you might be able to solve to actually define a theory. In flat space first, I'd be very happy with it.
Okay. Thanks again.